or so. But for those of you already here, welcome. Hope you're having a great day. Let's see, the closing days of September here in Texas, and we're still getting 97 degrees. So it's pretty, but still hot here. Hope it's great where you're at. I saw a comment flash up that somebody would like to say hello back, but they're muted. So sorry about that, but I appreciate the sentiment. We will have a question and answer at the end, and we will unmute microphones then. So, okay, the beeping sound seems to have faded. Yeah, okay, good. We'll get started then. So again, welcome. I'm Mike Riddle, and I'm glad you've chosen to join me today. And I've been wanting to do this presentation for some time. And I want to go ahead and give a caution in case you missed an email notification from us yesterday. Originally, I envisioned doing this as a general field problems with aerial fiber optic cables. I was going to discuss both OPGW and ADSS at the same time. There are some themes that share, but then of course each cable has its own unique aspects. And when I got into it, I realized it wasn't working doing it as a joint thing, so I split it. So today we're only going to talk about OPGW. No offense to ADSS. So if OPGW is not interesting to you because you only work with ADSS, you will not hurt my feelings at all if you wait until next month. We picked a date. Alexis, what was the date? October 26th? Is that
Yes.
right? Yes. So October 26th, we'll talk about field problems with ADSS. So today, just OPGW, although you'll understand some concepts that will carry over to ADSS as well, but you'll also hear the unique things that are specific to OPGW. So again, last chance to bail out. So here we go. So to begin with, this is an RCEP compliant presentation. That just means that we've met their standards. And if you want to get professional continuing education credits, we can do that through RCEP. At the end, what you'll have to do is, at the end of this, I'll talk about what to do to actually get the credit. You'll get 1 hour worth of continuing education credit. It basically involves taking a 10-question online test and passing it with 70% or more. So today's purpose and learning objectives, we are going to talk about what goes wrong with OPGW. And I want you to understand that the biggest source of damage to OPGW is when you're installing it. And we'll talk about some of the things that go wrong and how to avoid them from going wrong. We also want to talk about what goes wrong with OPGW during operation. And we're going to talk a lot about fiber strain, what it is, why it's important, how it affects OPGW, and how you can control it. And then we'll just close with a quick thought about, this is one of these things like, for those of you that are parents, you'll understand that when you find out that your wife or significant other is pregnant, and then you hear all the things that can go wrong, you're like amazed that children never get born. So today I was a little bit afraid I was going to talk about so many things that can go wrong that it's like, well, gee, why should I use OPGW? I don't think that's the case. So we'll talk about why things, problems don't just disappear by putting cable underground as well. Just a closing thought. And also, I should say this too, that, I started in Cab America and I'm part owner and president of the company. But all of these cable problems, they're from the companies I worked with before, or cheap inferior brand X cable. Yeah, I don't think we have, I can't recall any of such problems that I'm going to talk about with in-cab OPGW. So our agenda for today, we've already discussed the learning objectives. Presentation lasts about 50 minutes, and we'll close with about 10 minutes or so for questions. And I'll stay as long as you've got questions. So I'm happy to talk with you. All right. So when I began this, I thought about like just rooting it in my experience. But then I remembered that there's actually a UTC study that they did. They surveyed their members about problems with OPGW. And I realized that that was a good starting point, and that much of their data was pretty consistent with what my own experience had been. So they have a report that was published around 2017. It might have officially been 2018. And at the end of this, I will provide you with the link about where you can go and get that full report. This was done by the UTC's fiber optic committee, which was led by Mike Unser. So what they found was these problems: installation, number one, killer of cable, and then you see all of these others: manufacturing defect, accidents, gunshots. But notice number two is lightning. So you got number one, installation, and then your operational problems, that I'll call it. So things that happen after the cable is installed, or appear to happen after the cable is installed. Number one after the cable was installed was lightning, and then you see ice and freezing, and we'll talk about all of these major things. And then here down at the bottom, they looked at these and decided, was the issue an age-related problem, or was it not an age-related problem? So these just are like a further refinement of their results. But we're going to talk about all of this, especially the big three ones. So the installation, the lightning, and actually not so much manufacturing defect, but we will talk about that. Corrosion was what was in my mind. Excuse me, the ice and freezing. Okay, so first up, we'll talk about all of the installation related failures. So like the guy in the picture who's setting himself up for problems, you can set yourself up for problems during the installation process. And the single biggest thing that damages cable during the installation process are the stringing blocks. You can complete a poll and find out that the optics are already having problems. And so that's what I mean by it can kill a cable immediately, or sometimes the effects may linger. It may not show up until later. And the source of the problem is blocks that are too small. And the reason, the fundamental thing that's driving that is there is not enough bearing surface for the cable, or too much bending, or both. And basically it damages your optical unit, especially in the aluminum pipe type cable designs, where the pipe ends up flattened. So instead of having a nice round cross-sectional area inside the pipe, you end up with something that's more like an oval. That's not going to be good. Nothing good can happen. Only bad things can happen if the pipe gets flattened. One specific flavor you might think of blocks that are too small are blocks that are often referred to as banana blocks, or ganging blocks, or XS100 blocks, sometimes called X100 blocks. These are distribution class blocks, and all of these are trouble with a capital T. And fundamentally, what's going on there is that the actual rolling surface is too small. That's why I say it's a variation of it. So the solution to stringing blocks is to follow the manufacturer's guidelines. If you don't have a good guideline to the contrary, you can use 40 times the cable diameter as a good default. So if I've got a cable that's a ½ inch in diameter, I should use a block that's 20 inches root diameter. We'll talk about that on the next slide. Now, in some cases, a supplier may allow for smaller blocks. You can understand that there's a difference between pulling a cable 20,000 feet perfectly straight, no angles in the line. You're going 20,000 feet perfectly straight versus pulling in, say, 1,000 feet, like in a substation project. If I'm going a shorter distance, I might be able to get away with using a smaller block. But the way to find out if that's really okay or not is to talk to the cable manufacturer. And I do have to alert you that even this 40 times diameter, there are some cables and some manufacturers that may require you to use something larger. By the way, I represent NCAB on the IEEE Fiber Optic Subcommittee, and block size has been discussed a lot. And there are suppliers on the committee who make the case that sometimes you need even 60 times diameter. But those tend to be very large cables for very special situations. So I do fall back on especially for US utilities, that 40 times diameter is a good starting point. And then never, ever use banana blocks or gang blocks. One exception I'll talk about in a minute. And even then, that's not really a ganged block, or use a so-called XS100 block. So next slide, let's illustrate these. So here on the right, these are those bad blocks to avoid. The banana blocks are these two here, variations of this theme. You see small rollers, and the thinking is that, well, the cable lays across all of them, so its weight is divided across all of them, and somehow that's supposed to be good. It's not in the scope of today's presentation. I do discuss it in the installation presentation, why that isn't true. You basically have uh, a circle here, and if there's not enough bearing surface over that circle, then it doesn't matter how many blocks you use. If you don't have enough bearing surface on one circle, you don't have it no matter if you use 10, because the bearing surface just gets divided by the number of blocks that you have of a given size. It's not additive. So it doesn't matter that you have 4 rollers here. You could have 10 rollers, as I say. If they're too small, they're too small. It doesn't matter how many of them there are. Now, this one up in the right, this is that XS100 block. This is a distribution class block, and the root diameter of it is only like 4 inches or so. So it's just too small. And then this is a ganged block where you've taken 2 blocks. In this case, they're joined together by a yoke plate. But this doesn't buy you anything because of that fundamental concept that if the block root diameter isn't sufficient, then it doesn't matter how many of them that you have. So it doesn't buy you anything. I mentioned that there is an exception. The only exception is some lattice towers where you need a block to go from one side of the structure to the other side of the structure because the cable is going to go through the middle of the structure. And even in that case, the blocks on either side of the structure have to be the proper size, meaning they have to meet the minimum size requirement. But there's, in my view, there's still individual blocks, just one on one side of the structure and one on the other side of the structure, so that the cable can physically traverse through the structure itself. And then this key takeaway here is this root diameter that you see in the illustration here. That's what you've got to focus on. Now, in my hypothetical example, I said a ½ inch cable, 40 times diameter, you end up with a 20-inch block. there's a complicating factor in reality, and that is that the block manufacturers, they talk about frame diameter, which is the overall diameter of the block, or the actual wheel part of it, versus the root diameter. So what I don't mean to pick on them, but Sherman and Riley or Wagner Smith, what they'll call a 20-inch block might have a root diameter of only, like, going off memory here, 16 or 17 inches. So you've got to physically look at their table to confirm that what they call a block, that its actual root diameter, they do give you that figure, but you have to go look for it, and you have to verify that it meets the minimum size requirement for the cable that you're working with. Proper root diameter, absolutely essential. And as I say, within installation, its stringing blocks are the #1 killer of OPGW cables. So the next cause is excessive bending, and that's when you've exceeded a cable's minimum bending radius. So typically, that's going to be a figure of about 15 times diameter. You might see with the cable under tension, that's probably what you're going to see. You might see 20 times, but let's just say that it's 20 times just to keep my math easier. So that would be 10 inches, right? So 20-inch block or 10-inch minimum bending diameter. So if I bend the cable to 9-inch, I risk damaging the optical unit of the cable. Where does that happen? Typically, that happens when you're transitioning from a dead end to go down to a splice enclosure. You have to be careful to make sure that the arc that you make of the cable as it goes from the dead end to go down the structure, that you're maintaining that cable's minimum bending radius. The second time that it happens is during clipping in. So when you're installing the suspension units for the cable, what the crews will do will use some kind of a come along to get some slack in the cable. And if they're not careful in the process of getting some slack into the cable so that they can move the cable into the accessory, the suspension unit, they can inadvertently exceed that minimum bending radius. So the crews need to be trained to be careful to watch for that during that process. So as I say down here, the solution, be vigilant about maintaining that minimum bending radius, and use a generous arc when you're going from the structure or from a dead end down the structure to go to a splice enclosure. And the same thing, be careful during clipping in. Next, excessive tension during pulling in. Now, a cable supplier, they may limit the pull-in tension to 15% rated breaking strength, or I've even seen 10% rated breaking strength. But if a cable supplier told you that the tension needs to be kept under 10% of rated breaking strength during pull-in, they're telling you that in order to protect the optics. They might be being a little bit conservative, but that's kind of the intent. But and I have to respect that. If somebody tells you keep it to 10% or 15%, yes, you do need to watch that. But what I'm more concerned about when I'm talking about it here is when you're going even above 20% rated breaking strength, because somewhere above 20%, you risk causing sagging errors in the cable, because the initial sag charts or tables that you're going to work with to bring the cable up to sag assume that there is no cable elongation. But if I pull the cable too hard during stringing, the cable can elongate. And if it does elongate, I get into this situation where I can get the sag correct, but the tension is actually higher than what's on the sag table or chart, which is to say higher than what it was designed to be. Or I can get the tension correct, but then the sag is going to be higher than what it was designed to be. Um, either one creates a problem, right? If the tension is too high, then I'm potentially causing loading problems on the structure, which would get further amplified during wind and ice loading subsequent to the installation. If I have the sag problem, I risk violating clearance. I could also be reducing the shielding angle and thereby making the phase conductors more vulnerable to shielding failures, which is not good. So this is what I'm more concerned about here. So yes, pulling the cable too much, you could damage the optics. We already talked about that in the context of the stringing blocks, and kind of that's what goes on with the stringing blocks too when they're too small. I'll come back to that thought in a minute. So anyway, you have to maintain that whatever the manufacturer tells you, and it absolutely should not be above 20% rated breaking strength because of that risk of cable elongation that screws up your sagging. And the biggest thing that I see cause problems during pulling, other than the blocks, is anti-rotation devices getting stuck. Right? An anti-rotation device is sometimes necessary, but they're a little bit like the cable version of chemotherapy. They almost cause as many problems as they solve. And one of those problems that they cause is that the cable can get hung up in the block. And the natural tendency of the crews is to therefore crank up the tension. And of course, that can then lead to bad things happening. Cable damage, or the device can actually come apart, and everybody has a bad day at that point. So um, if the pole stops, the proper thing to do is to understand why. And if you've got an anti-rotation device, somebody should be following along on the ground and monitoring it. And if it seems to get hung up, you kind of need to hold what you got, go figure out what's going on, help it clear, and then resume the pull. Don't just crank up the tension on the puller. So next up is abrasion or scuffing, because that can create a long-term problem. If the cable gets marred during the stringing process and the aluminum coating on the aluminum clad steel gets damaged, then you're making the cable vulnerable to corrosion later. And what causes that to happen? Well, blocks being too small means that it takes more force to get them moving. And if the bearings are old or maybe not properly lubricated or something, that further increases that. And you can get to a situation where you're dragging the cable across the surface of a block. And then you're likely to damage the cable and have the potential for corrosion problems. Another thing is the block surface itself. Obviously, if the surface is not in good condition, if it's been damaged from previous pulls, then you risk having whatever damage is on the surface of the block transferring to the cable. That's not going to lead to anything good. And then, especially at angles, what I sometimes see is the OPGW needs to stay in the same plane as the block. And if it doesn't, it's smaller and lighter than conductor. And so it has more of a tendency to kind of ride up out of the groove and then get dragged along the frame. And then bad things will happen. The cable is going to get abraded, and you're potentially making it vulnerable to corrosion long term. And another problem is back tension at the payoff. I will illustrate that in a moment. It's a sign that there's tension down at a lower layer of the cable, and the cable rubbing it's against itself, which can lead to abrasion. A loose wind is also really bad because loose packaging can cause the cable to get sucked down from the outer layer into a lower layer. And then if that happens, first of all, there's a lot of abrasion that's going to be going on then. But if it really jams up and the pull is continuing, then it will suddenly release. And in the process of that, you can get a kink in the cable. And so that's a big problem when that happens. So the blocks, you need to inspect them before you use them. They need to be in excellent condition, not just good condition, but excellent condition, because as I say, they're the number one source of problems with cable during installation is the stringing blocks. They need to rotate freely. The surface must be smooth. It's not optional. And then another thing that I will share with you, in my experience, unlined aluminum blocks work the best. Every time that there have been stringing problems, like cables tending to ride up, or the cables got some torque imparted to it, whatever the problem is, every time it's been with neoprene or even urethane lined blocks. And the solution was to go to an unlined block and the problems went away. It's almost like a miracle there. Um, I think with conductor, because conductors tend to be larger and heavier, and conductors tend to have a softer uh, grade of aluminum, a softer aluminum alloy on the outside, 1350 aluminum, and it might even be annealed aluminum at that. You do need the line blocks for a conductor, but OPGW is a lot smaller. It tends to be lighter, and it has aluminum clad steel more often on the outside rather than a soft aluminum alloy like 1350. So the neoprene and facilitates the cable getting some friction, overcoming its weight, which is naturally lower than conductor, and therefore riding out of the groove. So again, my go-to solution for pulling problems has been unlined aluminum blocks, but some suppliers require the lined blocks, and you have to respect what they want. At least until you have a problem, in which case, if you asked me, I would immediately substitute an unlined aluminum block. But, you're taking some risk that they would then void the warranty. So you got to be careful about that, but hopefully you understand what I'm telling you. So I wanted to use this slide to illustrate one point here that you're probably not familiar with, and this is just too much back tension at the payoff, but I'll talk about some of the other problems too. I'm talking specifically here. If there's too much resistance to the cable reel rotating, the tension here will go up, and you will physically sometimes see the inside end of the cable pushing out from the reel. Informally, we call it squirting. It'll squirt out from the inside. And what that's telling you is that there is tremendous tension inside at the lower levels, enough to push the cable out. And so if I've got layers of cable on top of each other and they're moving against each other, they're rubbing against each other. And so you can get this abrasion, which in turn increases the risk of there being a corrosion problem. So back tension here needs to be watched. And what you're looking for is only hand tight tension. I think I say that here. I hope I did. Blocks rotate. Oh yeah, okay. Now I'm oriented myself. It's on the next slide. So back tension should only be hand tight. So what that means is that you should be able to stand here and with your hand pull on the cable, and you should get some easy movement. I know, I understand vague term here. What's easy movement? My easy movement is maybe different than your easy movement. How much is too easy movement? It's an experiential thing. You want it to move, let's say it should move about 6 inches up and down with no problem. If it's moving less than that, or if it's obviously tight like a banjo string, you need to loosen up. How can you loosen up? Often, if there's a braking mechanism, that's obvious. Turn down the braking mechanism. If there is no braking mechanism, it could mean that the axle is just not rotating freely, which you'll have to take a look at it and deal with it. Sorry, I don't have an easy solution if that seems to be the problem. The only other thing that you can do at that point, like if you know it's a great reel stand and there's not a problem with the axle and the brake is turned off, then what you're probably dealing with is a very long pull. And the only thing that you can do there is then go slow until enough of the cable has depleted so that the reel is rotating more freely. So best I can do in that situation. I'll just go ahead and revert to this concept about the stringing blocks because you see the diameter here. A smaller diameter, I guess it's going to be easier to use this circle. If I'm applying a force here, it takes less force to overcome the inertia of this wheel than it does if I'm applying it here at the axle. And that's at the heart of what causes problems with the smaller stringing block. They uh, they effectively require proportionally much more force to get them moving, and the smaller contact surface area. Plus, when you're stringing, you get a little bit of friction at each block. But with those smaller blocks, it's taking even more friction to get them moving. So the increase in accumulated tension necessary to overcome all of the blocks inertia goes up much more from one structure, from this structure to this structure to the next structure, and so on. So it accumulates much faster with smaller blocks. That's why they're so dangerous. So it's just another way of underscoring the point. Pay attention to your stringing blocks. They're critical to your success. So other things I talked about, blocks need to be in the same plane. I'll show you that on the next slide. We've talked about the cable being back tension at the reel stand being hand tight. And then the last thing, because I talked about the ability of the cable to pull down from one layer to another, you should check the reel wind before you start the pull. If the supplier sent you a reel of cable and the wind is crappy, you're within your rights to tell them your wind is crappy. I need you to rewind it. You really should. I know you got a project schedule to keep. Ideally, you would inspect the cable when it arrives. And if they try to send you a cable with a reel with a bad wind, that's the best time to catch it and get it fixed before you have a problem in the field. They may complain a lot, but if the wind is bad, you should insist that they fix it. Next thing is wood reels when they're rolling down the road on a flatbed truck heading to you. You know, there's a lot of bumps and vibration, road vibration that goes on and whatnot. So it is possible for the hardware to loosen up. So just tighten it up before you start the pull. Now, if a pull does start to go bad, if you've pulled through a few structures, you're committed and it's difficult to stop at that point. If that's already happened, my only tip for you is that you can try lubrication. Slick 50 has worked well. Now, we're not talking one can of Slick 50 and you spread a little bit. We're talking buckets of Slick 50 that you've got to pour on the cable wind to get some, to help things move more freely. The other thing that you can do, and you have to be really careful doing this, is to lightly loosen the hardware. Now, I know I just told you tighten it before you begin. Yeah, but if you've got a problem starting, you need for the cable to maybe move just a little bit. And one way to do that is to loosen the hardware just a little. Like I say here, about a quarter turn. That may help. Um, it's not a good situation to be in. That's I'm telling you, my experience, the best is along the lines of the best way to make the best of a bad situation. May not be good. If you do post stringing, find scuffing or abrasions, then you got to talk to the cable supplier. Take a bunch of pictures, send them a sample, or ask them to come out and take a look at it. What needs to be checked is, has the aluminum cladding been damaged to the extent that the steel is exposed? That's 100% what you're looking for in that situation. And then you can kind of make some best guess estimates of if you've lost service life. Okay. So I did want to illustrate this concept of keeping the block and the cable in the same plane. So you see here on the left that the block is hanging under the cable. So when the cable's under tension, the natural tendency is going to be for it to climb out of the block. So you absolutely need some support because that helps that not happen. You may not get it right, because it's a dynamic situation. What you would want to do in the field is have the block a little bit higher than the cable. So in a plane a little bit above the cable before you start the pull, so that the cable then comes up into the same plane. And arguably higher, a little bit higher would be better versus the situation that you have here. You can do that with a rope. You can do this with this counterweight system. There is a commercially available block support that's designed to go under, like what you see in this picture. All of them work to help, but you'll do notice this is a lined block. And I said earlier I don't line blocks, but this is the best picture I had. So key concept: try to keep the cable and the block in the same plane as best you can. And you need this especially at angles above 30 degrees, as I say here. All right, keep moving. Next up, incorrect sagging tension. So the sagging tension needs to be the way it was designed. If you're higher than the sagging tension, you risk causing fiber strain. We're going to talk about that a lot more later. If you're too low, then you're going to have too much sag. If you have too much sag, the cable could sag into something below it. That's not good. That's very bad. And you're also having the possibility of shielding failure. So the solution here is just absolutely follow the initial sag, the stringing tables or charts that you're given. Okay, next up, damage caused by tools and accessories. So this is a big source of problems too. These can take the form of a bad design. Yes, I know you're shocked. Sometimes vendors design products poorly. You probably never entertained that concept, but I'm sorry to tell you that that is in fact true. Sometimes it happens. Listen around. The big thing here is to work with the cable supplier and make sure that they approve whatever it is you're using. The next thing would be, so the design is bad. Another problem is that you selected something wrong. The size is wrong. In my hypothetical half-inch cable example that I keep using, if I use a dead end that's designed for 0.4 inch, I'm likely to have a problem, right? Or the wrong for the type of cable. There are some hardware that I would use on, say, a stranded stainless steel loose tube design that I would not use on an aluminum pipe type design. For example, specifically, single layer AGS supports, I think, are great for stranded type cable, but I would not use them on pipe type cable, just as one example. And then improper installation. So you can get the right hardware, and then the crews cannot install it correctly. The biggest offender that I've seen in that is bolted type dead ends, because in bolted type dead ends, what you're supposed to do is you tighten the bolts a little bit, and you're supposed to use a pattern when you do it, a crisscross pattern when you install these dead ends. So you tighten them a little bit, then you're supposed to go through and make another pass of tightening them, again in the crisscross pattern. And then you're supposed to do the final tightening and shear off the shear head bolts that are used on the third pass. So you're really supposed to do it 3 times using a crisscross pattern. What crews will do often is they'll get a ratchet gun and zip up one side and zip down the other side. And what ends up happening invariably when they do that is that the keepers end up cocked. And so the dead end will not develop full holding strength. Not good at all. So that's why I give them a special dishonorable mention to crews that don't follow the installation instructions. It's not only on bolted type dead ends, it happens elsewhere too, but the bolted ones seem to be a common problem that I've seen over the years. So your solutions here, you've got to get the cable supplier and the hardware supplier to work together as a team. Make sure that the cable supplier is okay with the hardware that you plan to use. I suggest, and this is controversial, it gets my controversial topic flag. I have a love-hate relationship. No, it's more hate relationship with bolted dead ends. I just don't really like them, but a lot of utilities swear by them, and so I tolerate them, I guess is where I land on that. I have claimed many times over the years, I challenge the notion that they are faster and easier to install, which is why people choose to use them. So I would say beware. Sliding wedge dead ends, I think, are always bad news. They tend to concentrate holding stress at the mouth. They've had a number of problems in the field, and I know of utilities that have used them and stopped using them because of the problems that they have. Shoe type suspension units with an open face design, we'll see this in a later slide. They seem to have problems collecting contamination. And I am not a fan at all of suspensions that don't use rods. These have become popular, and I think it's a case of being penny wise and pound foolish. So you're saving a few pennies on a suspension because you don't have the rods to put on. But those rods protect the cable. They help protect the cable. Why? They inherent, as I say here, they inherently provide less protection for the cable. Not good, right? What's the real benefit of this? Don't get me started. Next, last rather, for this, crews have to follow the installation procedures. And I strongly suggest that you actually include copies of the manufacturer's installation instructions for each and every item that you're going to use on your cable as part of your construction specification or construction package that you send out to your contractors. So on the point of tools, in particular, you should never use, and these tools often get used during that clip-in process to get some slack in the cable. So you'll hear them called pork chop grips or Chicago grips, but never use an accessory or a tool that has an elliptical or a triangular type shape on its mouth. You're just asking for crushing the cable and damaging the optical units if you do that. Grounding. Grounding creates a safety hazard for your personnel. So right off the bat, that's enough reason to make sure that you should be paying attention to your grounding and make sure that you have good bonding and grounding. Really, you need both. And it helps prevent lightning damage. I mean, there's a strong association with utilities that do a good job of getting low footing resistance, and not having a lot of instances of lightning damage. So grounding and bonding should be part of your design and hardware selection, and then they should be checked after installation. And if they're not, if the ground resistance is too high, then you should augment it or redo the ground. Augmenting meaning drive another ground rod and connect the two together. So of course that begs the question, well, what's good? And you can debate that, and it might even, one area might be easy to achieve something that it's impossible to achieve in another area. A rough guideline to a starting point, 50 ohms is what I've seen from some utilities. And I just want to go ahead and illustrate this. So bonding at the top versus grounding at the bottom. So the distinction there is that here what you're creating is an equipotential zone. So the cable at this point is at the same potential as the tower, and it's at the same potential over here. That potential, if there's not a good ground at the bottom, might not be zero. It could be some number, but at least everything is at the same potential. That's important for crew safety. Whether you attach directly to the cable using something like a PG clamp, which you see in this illustration, or you attach to the hardware and internally or some other way there's a connection to the cable, it doesn't matter. Both are okay by me. So this is just an illustration of doing it with a PG type clamp. This is an illustration of using a bonding point on the hardware itself. And then the ground, just to illustrate it, as I say, you should check this ground. If it's reading above 50 ohms, then you should augment it or rework it. Okay, so we've done all of our installation failures. Now we'll talk about operational failures. So first up, lightning. So you'll recall from the first slide that it was the second leading cause of OPGW failure, and it might be an immediate catastrophic failure. I mean, it literally burns through the cable. It could be medium turn, so you could burn through just a couple wires, but over time they unravel and eventually contact a phase conductor. Or it could be long term, so the aluminum an aluminum clad steel gets burned off and the damaged wires corrode, and then the cable fails in tension later. I've seen all of these over the course of my careers. So the solution, you really do need to have a cable design that's appropriate for your lightning conditions. And I do an entire separate webinar on that. For now, I will only say that I have seen that cables with an all ACS wire on the outside do seem to have a better track record long term than cables with a mixed wire configuration on the outside. I already talked about good, meaning low footing resistance is important. And you should respect your utility's experience. If you've had problems with conventional shield wire or the OPGW that you've been using for 20 years, well, then you need to do something different, right? Because what's the old definition? Insanity is doing the same thing over and over again and expecting a different result. So if you're having problems, you should look at that, try to understand what's going on, talk with different suppliers, get their opinion, and then figure out a solution. I'm telling you, there are utilities that don't have problems with lightning damage. So, the converse is true as well. So if you're having great experience, congratulate yourself and enjoy your day. So do draw upon your utilities experience, whether it's good or bad. Oh, and then as I say down here, your only other recourse is to try to appease the sky gods. Just to illustrate lightning damage here, so you see some um, strands that have been burned through. If enough strands burned through, then the cable can fail in tension. And that might be months later after something has been damaged, or even years later. Uh, enough wires are intact for the cable to survive day to day. But then when a big ice storm comes or something like that, the added loading pushes the cable to the breaking point. Here's a broken strand, and you can see it's already unraveled some. It's likely to continue to unravel if it's already started unraveling. And then eventually it can make contact with a phase conductor below, or just cause an arc when it gets close. So that's not going to be good. Just want to illustrate. So here's a cable, only ACS on the outside versus a mixed outer layer. And again, this does not mean that these are bad designs. They might be perfectly suitable in certain areas and function just fine. And there are trade-offs of design type, and it doesn't matter which of the major design types you're using. They're all vulnerable to this kind of a concept. So I'm not saying this design is bad. It's just that in some areas it could have more problems than this design, all else being equal. Next up, gunshots. So gunshots tie with water and ice for the second leading causes of operational failures. Now, sometimes the hits are intentional and sometimes they're only accidental, meaning somebody in one situation was directly trying to hit the cable, and in the other case, they were trying to hit something else but hit the cable by accident. So, you draw some small measure of comfort from the distinction. But usually, gunshots on OPGW usually lead to immediate optical damage, and there's not really a solution to it. You could build a bigger cable, I suppose, but is that still going to stop 30-06? I don't know. So what you can do is be prepared. So you can use an OTDR to pinpoint the location, and then you should have a good emergency restoration plan. You should have some replacement cable on hand if it's likely to be stored for a long time. It should be on a steel reel, and you need to have a few of the necessary accessories that you're likely to need. And again, you can also try to appeal to the gods for help. In this case, vengeance on the guys that shot your cable. A couple examples of gunshot damage. I mean, this nice shot dead in the center of the cable. Ice or freezing. This mostly happens with aluminum pipe designs, or so I thought. I recently had someone lead me to believe that this could have happened with a stainless steel tube design because of a weld failure. Uh, the gel should have stopped water from getting inside, so I don't know the whole story there. But in any event, the concept is really the same. Your pipe or a tube is breached, water's getting inside, it migrates to a point, or perhaps not. It doesn't even necessarily have to do that. It could be at the point of entry. Um, Freezing weather comes, the water freezes, and the process it expands and crushes the optical unit or the cable itself. So how does water get inside in the first place? Well, excessive bending during installation, alien vibration is a possibility, gunshot damage, or weld failure. So what can you do? Well, you can include water blocking elements in the optical unit design. Most cable suppliers who make aluminum pipe type cable do not include water absorbing material inside. Now, it might seem obvious that you should, but you can make the case that if a tube is breached, you're eventually going to have failure anyway. But my counter to the counter is that that's true, but you'll see a warning sign you'll see attenuation begin to creep up over time, and that should alert you that something is wrong there. You can go inspect, find the damage, and make a planned repair versus having a failure at 3 o'clock in the morning on a Sunday in February during an ice storm kind of situation. So I do think it is better to have water absorbing elements, whether it's tape or yarn, in the optical unit inside an aluminum pipe. Um, with that type of cable, you have to be especially diligent during installation to avoid the problems we already talked about. Proper motion control is also a must on all cables. SVDs are cheap insurance against problems. And then if you're using an aluminum pipe type design, I argue that the extrusion process of making that is better than the welding process. When you're making stainless steel tubes, those are always a laser welding process. Uh, Very high tech, and they should, if I was about to say always, but I can't speak for everybody, but they should have an inline eddy current testing process so that as the tube is being made, the weld is being checked. But eddy current works well with ferrous materials. It's highly debatable with aluminum. So maybe that's a possibility. I'm not sure. So here's an example of a pipe breach. Now, this was attributed to breaking during installation, but to me, it suspiciously looks exactly like an aluminum, excuse me, an Aeolian vibration fatigue break. But in any event, whatever caused it, water getting inside, nothing good can happen. I don't know the history of this, where this picture came from or anything, so I could be totally wrong. So. Next up, corrosion. We talked about, during stringing or lightning damage, could be a consequence of the environment. There was one particular design type that's not used that had a lot of problems with corrosion in the field. And there's one type of ACS wire manufacturing that is more susceptible to this problem. So we're back to good installation and good design, good installation practices and good design for lightning are necessary in coastal areas. Um, a lot of people don't like the stranded stainless steel loose tube in high salt environments. The cable is thought to have more to be more vulnerable to corrosion because of galvanic reaction. There are some reasons why that might not be happening theoretically. And then my own observation, I'm always a big what's your field experience kind of guy. I've not experienced any failures from corrosion on that design type where there weren't other problems going on. Um, and over 30 years, I've had positive experience, but that's what people say. So you should check to make sure that the ACS wire is made using what's called the conform process. It's really an extrusion type process. The other type is the powder type. There was one supplier that used to use that. I don't even know if they do anymore. It could be that they too have gone to the conform, but that process was vulnerable to microscopic cracking in the cladding, which left it vulnerable. Just want to illustrate this. This is actually from Buzzards here in Texas, um, and they were pooping on the cable. So the wires have corroded and broken, and you can see the aluminum pipe is actually corroded away, exposing the buffer tubes. So speaking of buzzards, others that were mentioned in the UTC report were buzzards, and that's specific to certain locations, and they tend to cause problems at or right on a structure. And I'm sorry, I just realized I'm going over time. I'll wrap it up as fast as I can. The best thing to mitigate that is some kind of protective cover. PLP has one, for example. Manufacturing defect is also mentioned in the UTC report. That's almost always poor optical unit design or the manufacturing of an optical unit, and it's causing fiber strain. A defective weld, that could be a problem. Your solution there is buy from somebody who's good. You know, it's that simple. Buy from a quality supplier. Now, age, brittleness were also mentioned, but I'm going to say that age alone should not cause problems with fiber. There has to be something else going on. If you look at a specification from the fiber suppliers like Corning, you'll see that there's a specification for heat aging and damp heat, and it's less than 0.05 dB per kilometer. So if your increase due to age can only be 0.05 dB per kilometer, then any increase above that is something else going on. It could be from corrosion, excessive tension, or fiber strain. Brittleness was also reported, and that too, I'm going to say, is either poorly made fiber, which is really to say a manufacturing defect, or they handled it poorly. Again, another version of manufacturing defect. It's not going to be temperature alone because fiber is specified to operate within this range, which is plenty for most, 98% of the world. And remember, you have this 0.05 dB per limit. And a lot of people will attribute it to water, but it's something of a myth that water kills fiber. Water and fiber don't mix, but these days, fiber always has some inherent hydrogen protection, and the gel that's used in the optical units of all of the designs, three types that are used and designs that we've mentioned today that are used, protects against water. And remember, you even have a damp heat specification, damp meaning water. So there's protection. So it can't be water alone is my problem. So either you had a problem with the fiber to begin with, or you've had fiber strain. And then accidents are just weird things, and the best you can do is have a good emergency response. But let's talk about fiber strain. That's how we're going to basically close out what's killing cables. So the concept is very simple. Fiber strain is when fibers have tension on them. And why do you care about it? Well, first you need to have some background here. Every cable has a point, a zero fiber strain margin point. Below that point, the fibers do not have tension on them. So the strain on the fibers is zero, and that's good. Above that point, the fibers do have tension on them. The strain is greater than zero, and it's a little bit of an exaggeration to say bad, but you get the idea. I'm trying to keep it simple here. At the maximum rated design tension of a cable, so that's the sometimes called maximum rated cable load or MRCL, there might be fiber strain or there might not be, depends on the cable design. So why do you care about it? Well, the major fiber suppliers have said that if the strain is kept at 0.2%, the probability of failure is very low. The exact number doesn't matter. So your expected life at 0.2% is 40 plus years. Now, this is a probability, it's not a guarantee, but that's what you're going off of, is that the probability, the expected life, would be over 40 years. But the higher the strain, you increase the probability of failure. Just going from 0.2 to 0.3% reduces my probability from 40 plus years to, I put 40 days. That's a typo. That should have been 30 days. You get the idea. And the effects of strain accumulate over time. So if I go above this 0.2%, even if because it's winter and I've got a wind and ice loading event, I do microscopic damage to the core or the cladding of the fiber. And when the strain is removed from the cable, that microscopic damage is still there. It doesn't just disappear. So in this example, if I did 1 day of strain at 0.3%, I only have 39 days left, which really should have been 29. And then the reality of OPGW in the field is, yeah, in summer, it's maybe 20% rated breaking strength or whatever you designed it to be. and it's only for a few months over the winter that your wind and ice loading brings it up. But that's cyclic loading. And fiber fundamentally is glass. It's a brittle substance. So cyclic loading and a brittle substance are not a good combination. So that's why you have to worry about it. Where do you get fiber strain in operation? Well, it's a function of the cable design. Each of the three cable designs that are used, and remember, I do a presentation, OPGW Engineering 101, where I talk about this in detail. They have ranges of zero fiber strain margin in this general range. It's inherent to the design type, how its geometry and how it functions. It doesn't mean that one design is bad or better than another. They're just different. And there are significant engineering trade-offs between them. So I start off with the design, the cable manufacturing. So I could have a design that's supposed to have a certain zero fiber strain margin, but I didn't make it very well. And it ends up with a lower zero fiber strain margin in reality. And I could have damaged the fiber during process by poorly handling it. So that's not good. And then the operating conditions. So you design for NESC heavy, half inch of ice and whatever the wind load is, but Mother Nature is what it really is. Instead of a half inch, if you get an inch of ice, well, you can expect more fiber strain. Or if your thinking is, well, in a typical year, we have X number of days, 5 days when the cable is going to be at 0.2%. But Mother Nature again chimes in, and maybe your cable ends up at 10 days at above 0.2%. So you could have more strain under real world conditions than what you were expecting. So what are your solutions? Well, as a general guideline, you want to minimize fiber strain. I call it here no strain, no problem. That's true, but in the real world, that's not. That's an ideal that may not be achievable. But you do need to understand what design type you're choosing and what it is. Your basic cable design guideline then should be keep the strain at 0 every day, so no ice, no wind, and make sure that it stays below 2.2% at whatever your max ice or wind load design criteria is. To do that, you have to get that information, and the cable supplier, I'm here to tell you, 100% knows this and will give it to you if you ask. We put it on our data sheet, so you already have it, but some manufacturers you have to ask for it. But you do need to remember that in the real world, if you know you're getting more ice and wind than what you've been designing for, then that should be factored into your evaluation, your sagging tension calculations, and use that criteria. The code itself is only a guideline. You should respect your reality. And I already mentioned, you can get this data from the supplier, and you should factor it into your cable selection process and your actual design process. On the cable manufacturing, you should do a little checking with your supplier to make sure that they're monitoring the excess fiber length, because that's a big source of zero fiber strain margin. They should have an inline process for controlling that, and they should be able to tell you that they get at least 0.25% or more. And then here's a big one. You should be looking at your operating conditions and adjusting based upon reality, because if you collect the weather data and you know that you designed for a half inch, but you collect the data and look at it and see that you're actually getting 1 inch of ice, well, that tells you you need to look at, well, what would the tension on my cable be under that condition? And what's the fiber strain under that condition? And you can use that data to then estimate how much strain you've had and how much time you've had above the 0.2% limit. And you can directly then calculate an expected life from that. It's really that simple. You can predict then, estimate when your OPGW is likely to have problems. And the IEEE subcommittee that I mentioned earlier, we are talking about working up a step-by-step guideline on how this could be implemented. But you can think it through or work with us now, and you don't have to wait for the IEEE is what I'm saying there. So, like I said at the beginning, I've presented a lot of problems, and it may seem to you like, wow, there are so many problems. Maybe I should just go underground. And I need to put those problems though in context. So OPGW does have an excellent track record overall, and it's really pretty simple. Good cable design with a good made with a good manufacturing process, and you're using good hardware to hold it up, and you're following proper installation practice. You can easily plan on 50 plus years of service life from your cable if you've got all of these factors working for you. And Ontario Hydro, they specifically think that they can get 70 years and that's realistic. Not a guarantee, but it's an expected life. And I need to remind you, underground cables have problems too, rats, and in particular backhoes. And when they go bad, they're harder and more expensive, and it takes more time to fix generally. So if you're trying to get fiber on your transmission lines, OPGW remains the go-to standard solution for doing that. I did mention about the UTC. So you can get copies of these slides and you can go to their website and find their report here. They also have a similar one for ADSS, and I will again be using that as a starting point for talking about the problems with ADSS next month. All right, and that's, sorry I've gone overboard. We'll open it up for questions now. And let's see, I need to go to chat. And Alexis, if you can let people use their microphone, but meanwhile, or in parallel, I will be looking at questions typed into the chat. Someone asked, can NCAP provide an OPGW installation guide? Yeah, absolutely. Drop me an email and I'll be glad to send you one. What is the general fiber count for the 40 times size block use? Well, that's all cables, all fiber counts. As a general guideline, that's a good one. Will this presentation be recorded and sent out later too? Yes, we are recording this, and thanks for the prompt to talk about this. So you'll get a follow-up email since you attended today, and there will be a couple things in it. A link to where you can find the recording. Do you provide a link, Alexis, to the slides, or do they need to respond and specifically ask for the slides?
They'll need to respond and ask.
Okay, so do what she said. So reply to the email and say you'd like to see the slides, and she'll send you the slides. A link to take the test if you want the continuing education credits, and you got to pass. It's 10 questions. You got to pass a 70%. And then a link for a survey. So give us feedback. What was good? What was bad? Ideas for other presentations would be great too. So, and then I see that Alexis already had answered that question. Sorry about that. For bonding, grounding, are you aware of any problems with bonding only one side of a double dead end with no splice? I mean, am I aware of any problems? No. Yeah, no. And, you can make an argument that if you bond on both sides, that you can act in the real world, you could get some circulating currents and, but I think that's the better practice, right? Because if I bond only once on one side, I do have the possibility of grounds going bad over time for one reason or another. So I would do it I would do both sides. I think that's the safer thing to do too, but being a bit of a purist there, I suppose. In case you get microbend within a span, what are the expected reasons for it? If you're talking about the fibers crossing over, and really, I think what's properly called a macro bend in the fiber or point-to-point contact, the main thing there is how the cable was made, the tube itself, and then if the tube was stranded, the stranding process there. So that's a little bit in the category of manufacturing defect. Now, one of the things that manufacturers will do sometimes is they'll put too many fibers in too small of a tube. And they'll tell you that it's loose tube, but they've really undercut the benefit of the loose tube construction. The reason loose tube has won out in all aerial cable designs is because the fiber should be, or if you're following the design concept, the fibers have the ability to move, which means that they can respond to changes in elongation. But it also means that if fibers have crossed each other over time, the movement should allow them to kind of relax and sort themselves out. If that doesn't happen, or that cannot happen if they don't have enough freedom of movement. So for any given size tube, there's a safe number of fibers that you can put inside, and when you exceed that, you potentially can have problems like what you're alluding to. The solution is more space, or what's becoming popular now actually is smaller fiber. So the standard fiber, 242 micron fiber, now everybody has got a 200 micron fiber or smaller. I think I know Corning has a 200 micron, but they also more recently have a 190 micron. And I've seen somebody come out with 185 micron, so that becomes another solution of making the best use of what available space you have. But fundamentally, that's what's going on there. It's kind of a variation of the manufacturing defect theme, whether it's a design problem or the way the tube was made. Let's see. Could warning spheres, vibration dampers be a source of damaging the OPGW? So aerial marker balls is what I'm understanding. Warning spheres, absolutely, they could be a source of damage. For aerial marker balls, I've seen ones that use a set of rods, and I've seen one that has like a bolted clamp on it. And because those things are actually rather heavy, I think it's a better idea to use them with rods. And I might even consider like adding a set of rods and then putting the marker ball on, even with its own set of rods. If you use the type that has like a more of a PG clamp or a clamshell clamp attachment, I would absolutely buy a set of rods and install the marker ball over a set of rods. Absolutely, 100%. Vibration dampers. I mean, a damper shouldn't be a source of damage on the cable. It's supposed to prevent damage on the cable. If it is, then it's likely a problem with the damper. Again, the way it's designed or the way it was made is causing a problem. A damper alone should not be a problem. Some damper suppliers, when it comes to OPGW, recommend and even require in some cases that you install the dampers over a short set of rods. And I'm not totally like on board with that, but I understand their complaint that they would argue that you're providing better protection to the cable and you're not diminishing the vibration damping performance. They've done testing. At least one supplier I know has done testing to confirm that you're not really adversely affecting the damping capability. So I'm not really I don't necessarily like it, but yeah, I think they have a good point there. So, thanks for the comment, a positive comment there. What is the best gel compound to be used with OPGW to avoid leakage inside the joint box? Okay, so um, the depends on the cable type. If the cable has a stainless steel loose tube in it, you should be using gel that's made specifically for use in laser welded stainless steel tubes. There are suppliers that use standard gel, and you can tell the difference immediately. Gel that's made specifically for OPGW has a slight color to it, at least. I mean, some of it looks like crude oil, and I try to avoid that type of gel. But Unigel makes a good product. I think it's called Unigel 400H, I think is the one that's specific for OPGW. It's got just a little bit of color to it, a little bit of brown color to it. And one of the things that's different about it from standard gel is that it's designed to uh, tolerate a higher heat level than standard gel, which you could have if a cable has fault current on it, or if it gets hit by lightning, it's going to heat up in the vicinity of the strike. So that gel I think is good and less likely to leak outside of the joint box. I'd have to think about it. I'm sure there are other good suppliers other than Unigel, but they're one that I know of that's good. Standard gel is perfectly clear, and you would use standard gel if you're using plastic buffer tubes inside an aluminum pipe. So there's in that type of construction, um, you want to be using a good quality gel, and Unigel I think sets the standard in that particular segment of our industry. So there too, that's what I would use. So um, yeah, I don't want to say that it's the gel supplier, but yeah, it's probably the gel supplier. Thanks again for the positive comments I see after that question. Let's see, let's keep going. In response to the question about dampers, typically dampers should be placed in the subspan between each marker ball. Yeah, that's true. Absolutely. In addition to those between the structure and the first and last marker ball, SVDs are a good answer to avoid clamping concerns from stock bridge type dampers. Yeah, for OPGW, I am a huge fan of SVDs. And then to come back to the marker ball question, yeah, that's a good point. The marker balls are so heavy that effectively, let's say you have a span and it's 1,000 feet, and just to keep the math easy, you put one marker ball in the center. You really wouldn't do that, but just I'm trying to illustrate a concept. That ball is heavy enough that it forces a node at that point. So think of it as effectively a virtual structure. It's just like you clamped the cable at that point into a suspension clamp. And so effectively what you have is two 500-foot spans, not 1,000-foot span. So if you were treating it and for whatever reason you put dampers only on one side, expecting it to cover the whole 1,000 feet, it won't happen. You'll effectively only get protection on one side. So you have to treat it as two 500-foot spans instead of 1,000-foot span for purposes of placing dampers. And that's one way to avoid problems with marker balls is to protect the subspan. So that means that if you were, in my hypothetical example, if you place two balls, and let's say you place them so you got 330 feet, 330 feet, 330 feet, close enough for this illustration, yeah, you have to treat it as three spans. And that means in that middle 330 feet, you have to have dampers there too. So that's that. Okay, don't see any more questions. I appreciate the questions. I appreciate everybody's time and attention today. Yeah, please look for the follow-up email and please give us some feedback and suggestions. Joe Renaud. Hey, Joe can change the sag too. Yeah, it does. Absolutely. You absolutely have to factor in the weight of marker balls in your sag and tension calculations. The major programs, PLS CAD and Southwire's SAG 10 program, both give you somewhere in there the option to say, I'm going to use marker balls and how many and how much they weigh. And you'll see how to calculate with marker balls. So, okay. Again, thanks everybody. Oh, can NCAB provide damper spacer recommendation? Yeah, we would work with a cable supply, a damper supplier to come up with a motion control plan if you need it. Yeah, happy to help. So once again, thanks everybody. Enjoy the rest of your day, and y'all take care. Bye for now.